We've already covered the AND rule and the OR rule, two very important rules. Now we'll talk about another rule, the binomial situation. The first thing I want to make clear, this is a problem type unlikely to appear on the test except as a very hard problem. So this is very important to understand about the material in this video. If you are the type of student who's aiming for an elite math score, if you really are trying to get almost every math problem right on the test, well then yes, you may see this, you need to know this. But if you're the type of student you're just trying to manage the basics, you know you're not going to get the hardest math problems right, you just want to make sure that you know the basic material so you get a respectable math score, well then definitely you should know the AND rule, definitely you should know the OR rule, those show up all over the place. This you may not even see. So you could probably completely disregard this, especially if you start watching this video and you find it too difficult. Don't worry, just let it go. It's not something you're going to have to worry about. So I want to make that very clear before we dive into this material because it is a little more difficult. I want to make very clear you should be deciding for yourself whether you should be wrestling with this or not. So what is the binomial situation? Binomial situation concerns multiple trials of the same thing. So we have some simple event like rolling a die or flipping a coin, and we're going to do that event several times. And so, of course, one of the assumptions is that all the trials will be independent. That's always true with dice and coins. And notice that it doesn't matter at all whether I roll one die 5 times or roll 5 dice at once. Whether I flip one coin 7 times or flip 7 coins at once. Both of those are completely identical as far as the probability is concerned. So, the probability of success in an individual trial is given or obvious from context. I think almost all the problems I've ever seen on the binomial situation on the test have been either about dice or coins, so it's usually obvious. What's the probability of flipping 10 coins and getting this many heads? So heads is a success. What's the probability of rolling this many dice and getting this many 5s? All right, well then 5 is a success. So success is determined. In something else, whatever they're asking the probability of, that is what we're referring to as, quote-unquote, a success. 2, the number of trials is decided beforehand. So, in other words, that's just the way that the problem is framed. The problem frames, all right, 10 coins are going to be flipped. So that's not up for debate. We know there are going to be 10 trials. So that's already fixed. Those trials are independent. And then the question is, within those 10 trials, how often does something happen? So for some number r, that could be less than n or equal to n, what is the probability of exactly r successes in n trials? So for example, what is the probability of flipping a coin 10 times and getting exactly 5 heads? What is the probability of rolling 7 dice and getting exactly 2 6s? Something like that. These would be the binomial situation. So how do we calculate this? Well, let's look at a couple examples. First of all, a very easy example. 3 fair coins are flipped. So, of course, these are all going to be independent. Very easy. What is the probability of getting exactly 2 heads? So, exactly 2 heads would mean that we get 2 of the coins showing heads, and one of them is not heads, so one is tails. And so, the probability of heads is 1/2, probability of tails is 1/2. All these are independent, so we can multiply. And that product equals 1/8. Now, naively, you might think, okay, that's our answer, 1/8. But we have to be very careful here. What are the different ways that this scenario, 2 heads, can play out? For example, I could get heads, heads, tails, or I could get heads, tails, heads, or I could get tails, heads, heads. Those would be the 3 ways it would play out if we were flipping one coin 3 times in a sequence. Another way to think about it, suppose we're flipping 3 completely different coins. Suppose we're flipping a nickel, a dime, and a quarter. When we flip those 3 coins, there's 3 different ways that we can get 2 heads with the single tail showing up either on the nickel or the dime or the quarter. And so there are 3 different ways for it to play out. These are mutually exclusive. Each one has a probability of 1/8, as we just figured out. So we add them. And so this adds up to a grand total of 3/8. And that is the probability of flipping 3 fair coins and getting exactly 2 heads. Let's look at another that's a little more challenging. Practice problem 2. 10 dice, each fair with 6 sides, are rolled simultaneously. So we're doing 10 different trials. Again, all of these are independent. What is the probability of getting exactly 2 5s among them? So in other words, what we're going to get one die is 5, we're going to get another die that's a 5, and then we're going to have 8 more. Doesn't have to make this very neat. 8 more that are something other than 5s. So the probability of getting a 5, of course there are 6 sides on the dice, so the probability of getting any number, probability of getting a 5 is 1/6. And of course the probability of getting a 5 on this one is 1/6. The probability of getting something other than a 5, getting any of the other 5 faces, well, that would be 5/6. So that is the probability for each one of these. Now, of course, all of these are independent, so we can multiply. So one way to say this is 1/6 times 1/6 times 5/6 times 5/6 times 5/6 times 5/6 times 5/6 times 5/6. Let's see, times 5/6 times 5/6. Okay, we could write all that out. That's a pain in the keister. Much easier to say it this way. 1/6 to the power of 2, 5/6 to the power of 8. Now, no one in their right mind is going to expect you to calculate these fractions. And in fact, what's probably going to happen is that the answer choices will just be written in these forms where it's printed like this, so you don't even have to do this calculation. You just have to recognize the right setup. Now notice, again, this is not the answer. Now we have to deal with the problem of how many different ways can those 2 successes, those 2 5s, be distributed among the 10 coins? Well, you may recognize that as a counting question. Now, if this is not familiar, you may want to go back and look at the combination video in the counting section. But essentially what we have here is 10, choose 2. Now, of course, we could figure that out relatively easily, but typically on the test, what I've noticed, they don't even expect you to do this. What they just do is they write the answer with all of this together, and this would be the way the answer is printed on the multiple choice. And so as long as you can recognize that, then you can answer the question. So they save you the work of doing the calculation on something like this. So now, let's just look at the general formula to summarize. The general binomial formula, we're going to say lowercase p is the probability of success on one trial. So for a coin, that's 1/2. For any face on a die, that is 1/6. N is the number of trial, R is the number of successes. So we have R successes, so that's why we have p to the R. We have success happening R times. If we have R successes, that means we have N minus R trials that are not successes. And so we have whatever is not a success happening N minus R times. And finally, we have to figure out how many different ways can those R successes be distributed among N trials. That's why we need the combination number. So I would strongly suggest that you don't blindly memorize this formula, but you actually think through the logic and understand why it has this form. That will give you the most success with it.